Okay, this section of the textbook is called the equilibrium constant expression. And basically it is an algebraic equation that relates the amount of products or concentration of the products and the concentration of the reactant, raising each to the power. In chapter 13, determining the rate constant K, or the rate law I should say, I stressed to you that you could not look at the equation and determine what the rate law was. The opposite is true for the equilibrium expression, constant expression. We use that to actually determine what the equation is going to be. So it's a equilibrium constant is the symbolized by a capital K with a C. Although in the next couple of chapters we're going to have different subscripts here to denote what this is. This just simply means for concentration. It's the value obtained for the equilibrium constant expression when equilibrium concentrations are substituted. So if I have a generic equation of A plus BB goes to form CC plus DD, and this is at equilibrium because of the fact that this is got the both arrows on it. Okay, I write the equilibrium constant expression here as the equilibrium constant C. Okay, and C just means concentration. The square brackets also mean concentration in molarity. So I have my product C, and I have it raised to the coefficient of the lowercase c. So this went here, this went here, and this went there. Okay, same thing for D, times the concentration of D raised to the power of D, divided by the concentration of A raised to the A over the times the concentration of B raised to the B. Okay, so the powers are the same as the coefficient in the chemical equation, and it's the right-hand side, or the products, over the left-hand side, which is the reactants. So here we're going to start just practicing by writing down what these equilibrium constant expressions are. Okay, so we start out, you have to write the full equation. So the left-hand side is Kc is equal to, okay, I want to look at my products over here, so I put a bracket to mean concentration, NH3, and then I raise it to the 2 because of this power right here becomes 2. Now that's my only product, so therefore I hit divide, and then I go over here to my reactants, I put a bracket for N2. The coefficient there is 1, so I don't need to write a power there, times the concentration of H2, and this one's to the 3rd because of the coefficient here is 3. So whatever the coefficient is becomes the power for the reaction. Okay, I suggest that you stop and try to do the bottom one next. Okay, we have the 2CO plus O2 goes to form 2 CO2s. Okay, so again, my left-hand side is Kc, and I have concentration of CO2 squared divided by concentration of CO, carbon monoxide, squared times O2. And that's all I have to do to write that expression. Okay, so now we're going to actually be using this process. So we're going to actually obtain equilibrium concentrations, equilibrium constants for reactions. What I have here in green is what is given in the problem. So I try to do this for the entire chapter, is I try to highlight how these problems are different. Okay, so I'm given starting materials, typically one of the molecules at equilibrium. I can, in the first problem we're going to do, all the molecules are at equilibrium, and a volume because it's concentration, so it has to be in moles per liter. So the process is to write the balanced equation. It's usually given to you. If it's given to me in starting materials, then I do the ICE table. Okay, this is referring back to the previous section. Find the C for the one in which you have both I and E. So this is the same process that we just did for the previous section. Apply that C for all of the, or change for all the reactants and products. Find the concentration. I do that by taking the moles that are given and dividing by the volume that's given. write the equilibrium constant expression, plug in those concentrations, and solve for Kc. So we're going to do a couple of these type of problems. Here's an example, okay, of the different values I could have for concentration. And I should not have changed that to pen just yet. Okay, so it doesn't, you notice here I have different starting materials, different amounts of the starting materials, okay? And my equilibrium concentrations are different depending on what I start with, but when I plug it into my equilibrium constant expression, my value is approximately the same for all of these, okay? So, and that's basically what this is. So this is set by this, and therefore, and then this determines that, okay? So here's our first problem. And so it says I have a 4-liter flask, okay? So I have a volume of 4.0 liters, okay? And it contained this, and this at equilibrium, okay? So I don't have, it doesn't say I initially had something and then changed it. So my equilibrium values here is the phosphorus trichloride, so the one with 3, is 0.0148 moles. The phosphorus pentachloride, so that's the one with 5, is 0.126 moles. And the chlorine is 0.870 moles, okay? And I have a temperature of 230 degrees C. And we're not going to use the temperature, but again, the equilibrium constant is in fact temperature dependent. Okay, so I already have my E's. I don't have to do the ice table. I already have my E's. So if you go back to this, I basically already have I'm basically already at step 4. Okay, I have all my E values, and now I need to find the concentrations. So we've kind of made this one a little bit easier by skipping steps 2 and 3. Okay, so I do that. The molarity is the moles divided by the volume, so I'm going to divide each one of these by 4.0 liters. Okay, and when I do this, this one becomes 0.0037. This one becomes 0.2175 molar. And this one becomes 0.0315 molar. Okay, so I have my concentrations. Now I want to write down what the equilibrium constant expression is. Okay, so it's Kc. It's my products, so it's going to be the concentration of PCl5 over my reactants, which is concentration of PCl3 times the concentration of Cl2. Now I'm going to plug in my numbers. So this is 0.0315. This is 0.0037 and 0.2175. So in my calculator, I enter this divided by that and divided by that, or, so in the calculator, it's going to be 0.0315, I don't need to have parentheses, divided by 0.0037, divided by 0.2175, oops, no parentheses, or it could be 0.0315 divided by, now I could use parentheses, 0.0037 times 0.2175 parentheses. Either way, the answer that you get is 39.1. Now, I don't normally stress the units. However, the homework system is going to ask you to put the units in. So if I look at this, I have molarity over molarity times molarity. So these two molarities cancel, and so I'm left with one molarity on the bottom, which is symbolized by saying molarity to the -1. And we will do another video that has several more examples, plus we're going to talk about a second type of equilibrium constant, which is that for temperature.